right, and we are live and broadcasting. Welcome, everyone. So today is going to be quite interesting. It is a new fundamentals episode in our Explore and Learn series. And the idea today is to explore hypermatrices. So in the last session, we did hypergraphs. Now it's hypermatrices. And they are connected in some way, potentially. I don't know, we might learn about that. So yeah, thanks for Carlos, Nick, and Richard for joining us today. And yeah, I'll hand over to Carlos.
Thank you very much, James. Thanks everyone who's following this fundamental series. Remember that we are trying to bring everyone up to speed with the concepts related to the research that is being conducted at the Wolfram Institute. So today we are going to be covering hypermatrices, and there will be a note on terminology and why we chose this particular name. Of course, because we're playing on hypergraph and all this sort of hyper motif that is very much proper to what we do. But otherwise, I want to make a quick recap of where we are standing in our fundamentals series. So remember that we are recovering the basic ideas of what lies at the foundation of many of the research projects here. So we had an introduction to hypergraphs. Then we now want to cover matrices and the generalizations that are relative to hypergraphs, which we call hypermatrices. Next time, we will cover rewriting systems. And probably after that, we will do something about causality or some fundamental notions in the idea of sort of causal dependence and things like that, which, as you can imagine, all these things are very, very much stringed. So hypergraphs lead into hypermatrices. Hypermatrices will lead into rewriting, as I will mention at the end of today's session. And obviously, rewrite systems will lead into causality and things like that. We might want to first talk about causality and then rewrite systems. But these things are largely interchangeable. Just as a reference, always come back to these videos if you want to see some basic explanations. With time, I want to announce that we should have more fleshed out courses that people can follow and attend and sort of properly learn and get training in some sense. But these are still sort of in the works. We are developing both the functionality and the infrastructure to deliver them and so on. But I do want to announce that this is part of our intention. We want to be a reference for some of the ideas that we work on. So, for example, Richard is making amazing progress on visualization of hypergraph rewriting in particular, and this is something that is sort of cornerstone of many of the things that we do here. So, Nick and I, of course, many of you know that we've been yes, interactive, not only visualizing, but interactive. That's very important, absolutely. So yes, and Nick and I, of course, have been busy trying to implement many of the notions of hypergraph theory and hypermatrix theory directly into Wolfram language, and that's also part of the progress here, part of the project here. So just to announce that these are some kind of starter dishes into what would be a main course at some point, not too far in the future, I hope.
So, yeah, that's exciting. So yeah, there's built some hype around learning about these hypergraphs and hypermatrices. I think actually trying to work with these things is the best way to learn about it. Just looking at the theory and seeing what somebody else has visualized is nice conceptually, but when you actually start wrestling with these things and trying to figure out, how to get the hypergraph into hypermatrix, you have to consider the different dimensions. It's the best way to actually get to grips with these topics.
Absolutely. And yes, Richard says, call this the hyper hype. That's pretty much the way to summarize it. So perhaps before we begin, we can recall our previous homework, just in case someone was curious. Let me address that in 5 minutes, and then we'll do the rest of the session dedicated to hypermatrices. So we had a question last time on Discord that I don't know if might be worth that I share it myself. So let me just I'm just sharing the Discord. So anyone who is on the chat, you can just access the Discord. If you don't have access to the Discord, just follow the link that you'll find the description, or James can also paste it in the chat. But this was what we asked last week, and it's going to be a motivation for what we're doing today. And so the first question was, can we define an adjacency hypermatrix for a ternary hypergraph? So last time we, as you can see here, we had a very basic notion of what an adjacency matrix was, which we're going to recall today. So don't fret. And so the question one was, can you generalize that for a ternary hypergraph? So for example, A or B in that picture. And the second one is, can you relate adjacency matrix multiplication as an algebraic procedure to some kind of graph question and answer or transformation or algorithm or procedure or something like that. And I believe there was a very good attempt, very good answer by Sam Rutke here. So they said, having trouble visualizing this, but figured it would look like some kind of 7x7x7 symmetric 3D tensor. So that's absolutely correct. So 7, I guess, was taken by counting some of the vertices. So I don't know if the count of 7 was directed to some number of the ones that we showed, because we had 5 and 6 vertices. So technically it will be a 5x5x5 or a 6x6x6 in A and B cases. And then for part 2, let's see what Sam said. If the adjacency matrix is equal to the product of the matrix with itself, you have an undirected graph. Yes, this is correct. If you have an integer of real entries, then the product of the adjacency matrix with itself will be element-wise square of the adjacency matrix. So these are correct guesses. So if Sam is listening, or any of you who actually attended this question, we are going to basically explain what the connection is at the end of at the beginning of the next explainer stream. So in the next Explore and Learn, where we do rewriting, we will solve this question fully. Today we're going to give the first component of the answer. So the answer is the notion of adjacency matrix. Of course, this is what Sam is getting at. I mean, it's just explaining that, the matrix being symmetric and when the graph is undirected and so on. And that's exactly the right intuition. Just as motivation, I think we can move on to a whiteboard here.
We also had one response from Dugan in the chat on the previous stream.
Right.
I've got it.
Did you post it there?
I'll share it on that same Discord quickly. It was a bit more of a mathematical response, but this was from Dugan.
For a 2-graph G with adjacency matrix A squared describes the connectivity of G by transversals along 2 edges. That's completely correct. So we are, as I said, this can be a form of spoiler or sort of anticipation. If you want to understand why that answer is correct, then watch our stream today and come to the next stream of the Explore and Learn to basically get the details and get the nitty-gritty of why that's the case. Okay. So for today, we are going to talk about matrices, or hypermatrices more generally. Let me start a whiteboard here. And I imagine James is capturing the window so that the relevant things are being shown.
Yeah, it looks good.
Can I somehow... You guys still see this?
Yes. Yeah. So
I clicked some stop presenting button because it was in the way, but I think everything's fine.
Yeah, can see good.
Fantastic. So I'm going to turn off my camera because I will use the same screen where I am working at as my writing pad. So you still hear me, right?
Yeah.
Okay, perfect. So, something is very off with my pen. Oh, what? That's very strange. I don't know what's wrong with my pen. Oh,
You got it?
I think so. How can I delete that?
What? The little dots?
Some highlighted stuff that is just unerasable.
I didn't see anything.
Oh, maybe I only highlighted locally for me. Okay, I'll move away from this position. That's very strange. Okay, it might just be some minor lag. Okay, I'll move away. I'll put the title here. Apologies for that. I think that, yeah. Hyper. Okay, so first of all, we need to talk about a terminology. Before the terminology, let's define stuff. We're mathematicians and computational scientists here. We need to be precise. Okay, so let's consider a field of numbers. And in fact, you might not want to think about a field necessarily. You just want something that I'm going to call a S set, which has an addition operation and a multiplication operation. So these are essentially number values. So if you want to think more concretely, you can think that S could be, for example, the Booleans, or it could be the naturals, or it could be the reals, or it could be complex numbers, or it could be some abstract ring. It could be many things. All it requires is a notion of addition and a notion of multiplication. And the reason why we call it an addition and a multiplication is that we are assuming the same axioms that they satisfy in the familiar settings, like as an and an and in Booleans, or as plus and times in integers, or reals or complex numbers, and so on. So that means that they are both. So just to summarize, so plus associative, commutative, with 0 neutral element, times is associative, commutative, with a 1 neutral element, and times plus distributive. Right? So it's the familiar thing. These are two associative commutative operations with their neutral elements, and multiplication distributes over addition. Okay? So it's just a familiar situation. The reason why I say this in the abstract is twofold. On the one hand, it is the minimal structure to recover the familiar phase of matrix algebra. But on the other, it's also, it's the same reason, but because it's the minimal structure required, and all these examples satisfy it, then you can replace your favorite number values, and you'll have meaningful constructions for everything that we will say today, right? So it's better for me to keep S as abstract, and I will say things like, A, B belong to S, therefore I can write something like A plus B, which is in S, or I can write things like A squared times B, then plus 2A, which is in S, and so on, right? These expressions are the kinds of things that we want to work with. And if you really are struggling with thinking in abstract, then just think that they are integers, for example, right? And everything will make sense. So something that maybe it's not made precise here. So by the way, this is what we called a semi-ring. And if you further assume that the addition operation has inverses, so there's such a thing as a -1, right? Then this thing is called a ring. So we might probably want to assume that we are in the context of a ring and not a semi-ring, but technically all the constructions that are going to be talking about today are valid for semi-rings. So you don't need to assume that you can subtract. So in particular, you can define these for natural numbers. That's part of the motivation to say that that it's a semi-ring. If you've heard of rings before, then you might think, oh, semi-ring sounds kind of more abstract. Don't fret. The natural numbers is the most direct example of a semi-ring, right? That's what you should have in mind. The natural numbers don't include the negatives, and that's basically what a semi-ring is a ring without negatives, right? So the first example of a ring is the integers. So when you throw the negatives into the naturals, you turn the natural semi-ring into the integer ring, right? And that's how you get there. So, but anyway, that's just some algebraic context for what we're doing. All right. So, okay. So once we have this structure, we have some numbers, some values that we can take over. We are basically going to say, well, if we have something that looks like a sequence, so let me just make a division here. So if I have something that looks like a sequence, so I is going to range from, let's say, 1 all the way to k, for k some natural number, right? So this is call it a sequential index, right? I'm going to be considering, actually, let me call this n, capital N. I'm going to be considering these kinds of sequential indices, and I'm going to call them indices just for short. The way you should think about these are sort of placeholder lists, right? So these are your, for example, in Wolfram language, you will find things like, you have something, you have something, you have something, you have something, right? And you have that. In more, so this is, Wolfram language. In math set theory, you'll have something like that, like a tuple with brackets or something like that, right? Which has a sequence. Clearly, you can assign position 1, position 2, position 3, position 4. You can clearly assign position 1, position 2, position 3 here, right? So it's it's a very fundamental notion of a sequence. It's something that carries this idea of running in a single direction. There's a notion of going forward and going backwards, and there's a first and there's a last. That's what these things mean. So sometimes we might want to call this a capital I set, right? Just for reference. Okay.
So just a quick question here. This K, is that does that still
refer? Just about,
okay.
Just I mean, K technically, K is a greater than 0. It's a number. So
okay.
It's the, sorry. This is not K anymore. Apologies. This is capital N.
Got it.
K
okay.
is no longer. Yeah. Sorry. Thanks for that. So what I'm going to consider here is a definition. So I'm actually going to give definitions for once. I know we are not very used to proper definitions here because many times we don't need them, but I'm actually going to give a definition. So an array, let me be very, a s-valued array is a map or assignment of the form. So you have some indices, I1, I2, up to ik. And an array A is just an assignment from the tuples of these indices, so the sequential order of these indices, into your semi-ring, into your numbers, right? So we will say that the order, the order of A is n1 by n2 by n3, whatever, by nk. right? And you know, this number of steps, the k steps, we also say that this is a k array, right? So the number of indices is a k array. So the way I would express this is by saying, you know, A will take some values of some indices. So remember, each of these i's is an index. Each of these is a sequential index. So it is ranging from 1 to some n k, right? Some number. So if I put some values in, right, you know, I'll say 2, I'll say 3, I'll say 5, I'll say 1, I'll say 3, whatever, right, all the way to whatever, 4 maybe, right? I put some values, some integer values. This is some numerical value, a that I call sub 3, 5, 1, 3, dot, 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 4, right? That's just a numerical value. Okay, so an array, as in this sort of functional sense, is simply a device that you give me a collection of sequential indices, and it produces a number, right? So in that sense, it is just a function, right? It's just a particular kind of function that maps into a particular number semi-ring. So your favorite things, if it's spitting out booleans or spitting out reals or spitting out abstract elements of some obscure ring, it doesn't matter. It is just assigning them to a sequence of indices, and an index is just an element of an ordered list of positions, right, from 1 to n for each of them. Okay, so I would generally refer to an array, so notation, an array A, so defined as above. I would typically refer to it as you know, uppercase A for the abstract object, the thing that represents the mapping as a whole, and to express both, sometimes both the abstract object, but also the particular values for each combination of indices, I would simply write it lowercase and with a particular selection of indices, I1, I2, all the way to IK, right? So I just gave you a very general definition of what I call an array. And the reason I want to do this is that this is very disconnected from any particular context. We are not talking about vector spaces. We're not talking about graphs. We're not talking about statistics. We're not talking about optimization problems. This is just some minimal definition that just requires choosing your favorite number semi-ring and, you know, some bunch of sequential information, these so-called indices, and then an array is simply an assignment of those things. So this thing is, in some sense, a mathematical table, right? Like the concept that we are bringing here is the concept of a table, right? Because and let me explain why. So why is this a table? So let's just give some examples. You know, after definition, there should always come some examples that give us some intuition, especially when there's some indefinite variable like k here, that, you know, the order of the array can be quite daunting if you think of, you know, an indefinite number of indefinite length indices. Okay, let's see how this works. Let's think of one array. I want array value in, let's say, the integers, just for a change, right? So what is a one array valued in the integers? So, well, this means that I'm going to have one single index set. So A is going to send a single index set into the integers. So my index set is going to be, I'm going to choose it, I'm going to choose an index set of length 3. So in this general definition over here, I'll put n equals 3, right? So I'll say 1, 2, 3 is my index. So my index is just a label that can run from 1, 2, or 3, right? It's just that. Okay, so what is A? Well, A is just an assignment that is going to send, you know, A at the value 1. That needs to be an integer. I'm going to give it the value 0. A at the value 2, that's going to give 5. A at the value 3, that's going to give -7, for example, right? So this information fully captures what I would call A sub I is, right? A sub I is the array. And in this case, because the index set is just 1 to 3, all I need to say is what are the values of this array for that. So if you arrange this into some expression, like with some brackets, just for order. So in the brackets, the sequential order of the spaces is always 1, 2, 3, etc. So you know, this is mimicking 1, 2, and 3 in positions. I will write, you know, 0 over here. I would write 5 over here. I would write -7 over here. right? And of course, this is familiar to everyone. This is the typical name that in computer science and programming, people use for arrays. So that's how you recover your. I mean, some people might call this vector. I am actively avoiding these names for now, so just bear with my notation and my terminology for a second. All right. So this doesn't look like a table. That looks like a list. So yes, one arrays are lists. This is all good. Now, what about a two array? So let's say valued in the booleans. Why not? Okay, let's do this one over the reals, for example. Who cares? So now I'm going to have, let me call it B, for example. I'm going to have two indices. Let me call them I and J. Then the take values in R. So I'm going to say that my I set is, for example, 1, 2, and 3. And my J set is just 1 and 2. Okay? So all I have to do is, for each combination of values of I and J, this needs to be a real number. So the convention typically is that I would assign like the first index here as a row, right? So I will just write it like a list, and then J will be a list of lists. So it will be in the perpendicular dimension on my notation. So I would go for I in this direction. So I will do 1, 2, 3. I will go for J. I want to write it maybe here. In this direction, I'll go 1 and 2. So I'll write the brackets just like before, and I will just keep track of those positions, right? So I equals 1, J equals 1. That's this position. For example, that could be, I don't know, pi. I equals 2, J equals 1. That would be minus 2. I equals 3, J equals 1. That will be 0. I don't know. And so on, right? So I'll just fill in with, E squared minus 1/4 and 5 or whatever, right? So this is a two array valued over the reals. And so the abstract element here, just like before, the abstract element was a way to represent all of them for all the possible values of I valued in the integers. Now it's for all the possible values of I and J valued in the reals. Okay, so that's a two array. So of course, this is what a lot of people might call the list. So I'm just going to put some names that people typically assign to these things. Actually, let me do the three array example, and then we will talk about terminology altogether. So as a final example of a three array, just for visualization purposes, a three array valued on the booleans, for example, would be something like this. Let me call it C. Now, I don't know, let me just make it regular. And so I introduce a name here. If you want to remember, we say an array is regular when, so this is regular. So let me put it here for summary. C is regular because we are taking the same index several times. So the same sequential index set that here generally could be different ones, I1, I2, I3, etc. If they happen to be all the same, because in particular they happen to be all the same length, because that's the kind of convention we're taking, then you call them regular, right? Or sometimes people might like to call this also cubic or square. So sometimes it's kind of an easy, more direct word to use, square or cubic, but it's not so convenient to use square and cubic. You might want to reserve those terms for algebraic statements, like as in algebraic square, algebraic cube, for multiplying 2 times or 3 times. So anyway, but we'll call it regular. And what is it? Well, let's say that I is simply 1, 2, 3 again. 1, 2, 3. So again, ijk will have to give me some Boolean values, so it will just be 0 or 1. And so now, if you want to visualize what a three array is, I will use the same diagram as before, but I'll have I in this direction, I'll have J in this direction, and I'll have K in a perpendicular direction, sort of in a third dimension. So, I will write this as a cube just for ease of visualization. I can do something like that. And then, in each direction, there is, one, so I'll write it here. There's 1, 2, 3 position, there is 1, 2, 3 position here, and there is 1, 2, 3 position over there. And all I have to do is fill it with zeros and ones, because it's just valued over the Boolean. So I'll do 0, 1, 1, 0, 0, 0, 0, 1, 1, then 0, 0, 1, 1, 1, 1, 0, 0, 1, and 0, 0, 0, 0, 1, 1, 1, 1, 1, for example, right? So just to make it a bit more clear, the way this looks really is like this, right? So it's a cube. Oops, there's a pre-skewed cube that has divisions like that, right? So it's 3 by 3 by 3 as a grid. Okay. All right. So these are what 1, 2, and 3 arrays are mathematically. These are just definitions. So let me maybe I can use a different color here. Can I change? Yeah. So I'll use purple to write down. Oh, sorry. Why can I just? I will use purple to note some words, some names that people attribute to these things. So one arrays are often called lists. They're also called vectors. They're sometimes also called, maybe less often, but registries. This is a little bit more contentious, but anyway, some people might have used
tuples. Oh no, is that a different concept?
Oh yeah, definitely tuples. Yeah, these are some names.
Does it help to think about scalar at this point, or did we skip over that deliberately?
Okay, actually, that's a good point. That's a good point. So to complete my discussion, what about zero arrays? Does that make sense? It doesn't according to my definition, because I define n to be greater than 1. But sorry, I defined the number of entries to be finite, because otherwise there's no statement. But you can, by convention, say that a zero array. I mean, a zero array is not an array in the sense that I defined, because it's not a map from nothing to something that doesn't exist, right? But for convention, we can say that a zero array is the notion of what, in category theory, you would say something like an initial element or something like an initial object kind of situation where you have your map is one single assignment. Right, and so when your map is a single assignment, that's the same thing as picking out an element of your possible target space, right? So a zero array, we typically identify with an element in S. So yeah, it's a good point, because then in this kind of list of terms that people attribute to things, I can certainly attribute to an element in S the word scalar, or the word number, or the word value even.
And what about element itself, the word element?
Well, I mean, element, yes, but element, it's far too general.
Okay.
It's far. I mean, that's the set theoretic term to describe membership in a set, right? So element, I guess you could list it here. We are just being sort of exhaustive. People do mention element, but it'll be very strange if there's something that can be called a number to call it an element when you're just referring to its nature of a number. It's a bit strange.
Scale is the most common, right?
Well, I'm not making judgments about these terms yet. I want to give my piece on names, because that's an important one, because there's a lot of dispelling to do here. So let's not slant the discussion in any particular way. Array is a pretty neutral term because it just refers to something that is more or less intuitive, like an array of things, and its meaning in most of computer science and programming languages is very literal to this mathematical definition. So it is quite a neutral stance. And then the thing is, arrays show up in many different mathematical theories, and they have quite different meanings in those contexts. So that's why I wanted to do some kind of bookkeeping. Sequence, yes, thanks, Richard. That's a good one. Yeah, sequence is a good one. For this one, oh no, same problem as before. No, my pen, I don't know, is acting up. Yeah, I don't know how to fix it. Previously, it was just give it time. All right.
So is that so just to disambiguate the term array? Is it because arrays can sometimes be can be the same as a list if in the computer programming?
Okay, that's where I'm going. I'm just my pen just stopped working for a second. Can I somehow? Yep, completely stopped working for some reason.
Turn it off and turn it back on or something.
It doesn't have on and off, unfortunately. Before, I don't think I did anything specific. I just stopped. It just worked on its own. Oh no! Now it's the highlighting again. Why?
Just bear with us. We're innovating on our tech stack here. So the Zoom whiteboard we realized in the last session was very useful. Also, we're going to be saving these images afterwards into places where people can refer to the whole image. So if there's something that we skipped over in the video, we'll be able to share that with you guys later, and you can go and look at the little small drawings that you might have missed in the video itself.
Do you still see the whiteboard?
No, whiteboard's gone now.
Oh. You see it now, right?
Yes, it's restarted.
So I tried the age-old trick. Let's see if this works. Element. It did the trick. All right, so sequence was one. Oh, not there. So Richard mentioned that sequence is also a term here. But then if we go to two arrays, so these were names that people often give to lists. But if we go to two arrays, we will find definitely the name matrix. We'll find the name table. We'll find the name form. We'll find the name. I mean, it's going to show up down here already, so I'll put it down here just for things. This a lot of people will call this tensor. When we have 3 indices or more, right? What else? Can you guys think of other names?
Hypermatrix? Oh no, because it's specifically for 3 dimensions, right? So you need to be specific.
Yeah.
Cube? No. You mentioned that's not right there.
No. What's
So if it's specific, isn't it 3 or more? Because tensor is 3 or more, right? The tensor can be an even higher. So at this point,
no. Tensor can be in the lower ones. I wanted to put it in the one that most people use it. Yeah. So, okay. Nick, Richard, can you think of some other names that people give these things? I'm just trying to, circle around some names just for the sake of
multidimensional array.
Okay, sure. Let's bring it. So sure, yes, like multi-dimensional array. So because this is just a note about terminology and not about definition, we define these things as arrays technically. But yes, definitely this will be. I mean, here will be array as well. A lot of people will give this. Actually, some people might call this a transformation, or even a linear map. Yeah, even permutation, even, I don't know. So anyway, I'm just trying to give some context to my disclaimer, my notational disclaimer. So
Cuboid?
all this, yep. Say it again.
Cuboid for a 3 tensor.
Cuboid? No, I don't think so.
ChatGPT gave me that one.
I don't know. Maybe some people do, but the point is not.
I did see it, but I didn't. I saw it on some page, but I remembered your earlier remark not to confuse it with cubes and squares. But it is technically not.
No,
Yeah,
if
it's
someone's used it, I mean,
Yeah.
I'm not. This is not. It's not right or wrong. If someone has used it in some context to refer to order 3 array, then I'm just circling the terms. It's not. It's not about right or wrong. Okay, but I think this is good enough for my point. So the point that I'm trying to make here, which I already alluded to, is that arrays, the notion of array is very, very basic, right? It only took me 5 minutes to write down the definition up here, take some sequential indices and just value your ordered list of indices over some numbers, right? Over some number semi-ring. It's a very primitive, it's a very low tech, so to speak, definition. There's no big theory behind it. There's no, there's nothing very sophisticated going on in the background. I don't need to give you several pages of definitions and lemmas to introduce what an array is. However, if I were to define a tensor, I would certainly need that. So that's something that it's important to clarify here. And I'm glad that we did this Hypermatrix explain and learn live stream, because this is something that I've been complaining about for years now, and it's great to have a forum where it is the most important thing to say, that not to confuse a tensor with a matrix, with a hypermatrix, with an array, with a cuboid and all these kinds of things, with a linear map and so on. So I
always
won't go
bothered me when TensorFlow came out. I was like, oh my god, no.
yeah. The fate was sealed the day that package became so popular. The fate was sealed for the terminologies. So I won't go into details. I mean, in the future, I'm sure that we will have the chance to do another Explore and Learn about linear algebra or multilinear algebra, because sooner or later, this is going to be relevant. Of course, that being the foundation of a lot of the machine learning algorithms and data processing algorithms that are most popular today. And of course, all the connection to hypermatrices and all the hypergraph science that we do. But as a first, or as a, I don't know, as a disclaimer, warning to what will come in that Explore and Learn live stream, it's very important to note that in the definition of an array, which is all we need for our purposes, when I'm going to define hypermatrices below and their connection to graphs in a second, and that will be basically what will lead us into the next Explore and Learn next week. But for all we need, this is sufficient. Arrays being assignments of numerical values to table-like arrangements of sequential indices, that's all we need. If we were to define something like a tensor or a linear transformation, or something that, an expression of a bilinear form in terms of basis elements or elementary, or actually, yeah, I can also include structure constants. That's a good one. If you're a physicist and you've ever seen the algebras, you might remember that some 3 index objects that are basically the components of the bilinear operation that your algebra operation is in your space, or the Lie bracket is in your space, or whatever. So those are structure constants. So there are many things, right? So if you were to give meaning, concrete mathematical meaning, to any of those terms that are not arrays, you would have to specify a lot of background information. And by a lot of background information, I mean, so just to give it the quick example of vector, right? So a lot of people will say, wait, come on, that's just a vector. A lot of people in data science will just, or computer science will just say, oh, that's a vector, 0, 5, -7, that's a vector. a vector of 3 components or something. Okay, so if you want to give vector the meaning of a vector, then you need to say that a vector is an element of a vector space, right? That's what a vector is. And if you want to define vector space, you would realize that then you'll have to go through, okay, so a vector space is a set that has an abelian group structure, then it has a set of scalars, which is typically a field, and that field has an action on the abelian group that has whatever, 6, 7, your favorite set of axioms for vector spaces, 1 times a vector is the same vector, minus a vector plus minus the vector is the 0 vector, all these, all these properties, right? The fact that, addition of vectors is distributive with respect to a scalar multiplication, and all these properties of vector fields. You need to encode that in a very precise way. And only then, when you have that encoding, you say something like, okay, choose 3 independent elements of your space, and then express any other element in terms of those 3. Then you would have something that looks like a list of numbers, because you would say the first element of your basis needs to carry a scalar multiple, your second element in your basis needs to carry a scalar multiple, and your third element in your basis needs to carry scalar multiple. So when those scalar multiples happen to be 0, 5, and minus 7, then your abstract vector element expressed in that particular basis will be expressed or will be represented by this particular array, right? So that, or what people would call in linear algebra, a matrix representation of the vector, or a basis-dependent representation of the vector. And so it's very, very important that if you change your basis in that space, suddenly the numbers will change, right? I rotate the base and it will change. Not only will they change, but if I perform all the possible base transformations, basically meaning that I choose any 3 independent elements in my space, you would actually recover all the possible combinations of numbers in those 3 entries. It's not only that they will change, but in all the possible base expressions of your vector, you would actually find all the possible 1 arrays of numbers, right? So it's not only that a vector is not only a 1 array, is that a vector is in fact an infinite set of 1 arrays, right? Because the information of the vector is not encoded in the array. It's encoded in the array plus the choice of bases in that vector space. So this is just, as I say, I don't want to go into the weeds of this because today is not about linear algebra, but that's the level of technicality to just say that a list is not the same as a vector. So if you replicate that discussion for matrices, then I would say that a matrix, which is a 2 array, by the way, I am making that connection here explicit just for future reference, because that's the second last part of the session today, is that I am actuating these 2 things, a 2 array. I am adopting the notation as matrix. That's a good enough notation. So I would never claim that a matrix is the same thing as a linear map, although that's what a lot of people grew up thinking, high school linear algebra, and then, undergrad linear algebra, and, introductory courses to linear algebra do make this connection very, very clearly. The same sort of technicality, but even with further bookkeeping requirements, is necessary to connect a matrix with a linear transformation. So in that case, you need to choose 2 different bases in the source space and the target space. And again, these matrices will be transformed by all possible invertible matrices by conjugation and so on. So there's a quite non-trivial amount of information when you say that this particular matrix corresponds to a particular linear transformation. It says not only you will have more than 1 expression that represents the same transformation, but all of them are going to be related by a group structure. So all of them can be combined with each other to form a third one with associative property, inverse, and so on. Like, it has a lot of information. The fact that a 2 array can be thought of as a linear map has all this sort of linear algebraic machinery that is usually swept under the rug. And that's why I think there's no real justification mathematically to say oh yeah, don't be pedantic. Matrix is just a linear map. We can just think about it as a linear map and forget about it. When you are really thinking about the foundation of your algorithms, or you're trying to make progress at the core of your systems and your programs, these things need to be very clearly delineated, right? A linear map, if you want to use a matrix as a linear map, you need to assume that there is a structure of the linear algebra machinery in place. Otherwise, we are missing information, right? So just as a warning, and by the way, that's what leads into a tensor. A tensor in the notion in the tradition of linear algebra is a generalization of a linear map, right? So it comes from that tradition. So a tensor is just a particular kind of linear map, in fact, that has a specific arguments. And so a linear map requires a lot of information about the linear algebraic context. So when that is not provided and all you have is a table of numbers, you should not be claiming that you have a tensor. That being said, I'm not being particularly combative to not use the word tensor. If this is by fact of common use, 3-array or higher order array has been synonymous with tensor, that's fine. It's no problem. I'm not saying that words should be kept in this kind of semi-religious way, but it is very important to know that technically a tensor is much more than a 3-array, right? Which is to say, a linear map is much more than a matrix, which is to say a vector is much more than a list of scalars, right? So all these are the same statement, basically. And this was just a big warning that that is not always clear in a lot of applications. We are not going to need it in our particular setting, in what we do here today specifically, and in the next couple of streams for sure. When this becomes relevant again, we will flag it, we will explain it, don't worry. But just as a word of warning, that there is a very widespread misunderstanding, well, at least terminological misuse of the terms, that when you're involved in research like we do at the Institute, which is more foundational, is more about rethinking how things work at the very core and not just finding some quick application about existing algorithms, we need to be very careful about these notions, right? We need to be very diligent with our definitions. Anyway,
that's great.
Yeah.
Some
questions, some final thoughts about this before I explain what hypermatrices are and basically give the entry to the next live stream.
Yeah. So I had maybe just for the summarized soundbite, you once explained to me when I asked what is the difference, why use the term hypermatrix instead of a tensor, and then you broke it down in like quite some detail. So maybe just for the concrete reason, why do we prefer the word hypermatrix instead of tensor?
I'm going there. I haven't talked about hypermatrices yet. So these were arrays. So these were the notion of an array, right? This is the term that I am taking ownership of, and again, similarly, I am equating one array with list, for example, right? Same way I'm equating 2-array with matrix. Actually, technically, I should include myself. I always have this tendency of not including my own work in presentations. I mean, we call these things cubices, so cubics, right? So I will equate the word cubics with 3-array. Typically, regular 3-array, but whatever. It's good enough for the sake of explanation.
So it's got that same rhyme with matrix, that like
yes,
iteration.
Exactly. It's to rhyme it with matrix. It's just cube matrix, because people were calling them cubic matrices, and I said I'm not saying cubic matrix every time that I want to refer to this, so I'll call it cubics. But those are just arrays. So what the hell is a hypermatrix? Hypermatrix wasn't the title for the stream today. So what are these things? Hypermatrices are the algebraic encoding of the adjacency information of hypergraphs. So just if you want some quick definition, a hypermatrix, let me say it like this, hypermatrix encodes the, let me say faithfully, encodes the adjacency data of a hypergraph. So to make sense of this, yes, Richard, one way to think about it is as an abbreviation of hyperadjacency matrix. But the reason why I want to coin something that is different, that is not a matrix, is that hypermatrix is going to have its own meaning, hopefully, and this is a theory that we are in the process of developing, but hopefully we'll have a theory that is roughly parallel to that of hypergraphs. Okay, so to motivate this definition, and by the way, this is basically the ending of this explore and learn. This is the sort of target point that we want to reach. We are going to recover the case of graphs. So this is, two regular hypergraphs, also known as graphs. Okay. So this is what I said. The first piece of the answer to the questions that I posed in the last one is going to be given today. Now it's when it comes. So how to extend this notion. So last time you remember that we were introducing the notion that when you have a graph, something that looks like that, let's make it directed so it's even more obvious. So you could have something like this, maybe something like that, and then something like this, and then something like that, okay? Or maybe even with a self loop. This, if I call this 1, 2, 3, 4, and 5, I could encode in an array structure, right? The reason is that, remember, an array simply is a form of table, so it can just give me a combination of data structure of pairs in the case of a 2 array, right? So if the elements of a graph, the edge elements of a graph, right? All the edge structure of a graph is essentially pairwise information, right? So the information I have as this, basically 1 goes to 3, 2 goes to 3, but also 3 goes to 2, but also 3 goes to 4, but also 3 goes to 5, and also 5 goes to 5 itself.
Is that relationship information? Or how do you call that information?
Yeah, some relationship information. So this is what I would call the adjacency information, right? Because this is telling me what vertices are adjacent along an edge of my graph. That's the language. That's how the languages are defined. So being adjacent means that you have some space, interstitial edge space between the 2 vertices, and so you say that 1 is adjacent to 3, right? So the way to encode this is, of course, as a 2 array, right? Because I will have to encode in the I index, you encode the source of the adjacency relation, the directed adjacency relation, and in J you store the target. Okay, and so when the source is 1, 2, 3, 4, and 5, or when the source is, or where the target is 1, 2, 3, 4, and 5, then we get basically the information of the matrix. So, is there something that goes from 1 to 1? No, so we write a 0. Is there something that goes from 1 to 2? No, so we write a 0. Is there something that goes from 1 to 3? Yes, so we write a 1, and so on, right? So I don't know, 0, 0 here, 2 is only has with 3, so there's a 1 here, 0, 3 goes to 2, goes to 4, and 5.
So it's directed in terms of I going to J or J going to I?
I is the source, J is the target.
Got it. Okay, source.
That's what those names refer to.
4, 2, 5.
So
okay.
4 is not going anywhere.
3,
First,
2, 5. That's a 1.
Yeah.
3, 2, 4 is a 1. Oh, no, that's wrong.
No. Yep.
Oh, this is also wrong. No, that's right. 2 until 5 is no. And 1 to 1 is no. Okay.
Yeah. So okay, so clearly this object here is a matrix. And this is, of course, called the adjacency matrix. So this is all well and good. If you had an indirected one, you could say that you can encode the symmetric version of this for the same information. But the point is, what happens when you generalize and you have something that has higher arity relations between the vertices? So something that might look like this. Actually, I want to draw the same. So 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5. But imagine that I now have something here. I have something here, for example, right? Then what you want to encode, and again, this could be undirected or whatever. What you want to encode is the information that 1, 3, and 4 are together, right? So 1, 3, and 4 are together. And you also encode the information that 3, 2, and 5 are together. So what you do is you say, well, I'm going to set up an array that has, I, J, K, in all the directions as the three possible vertices of my structure. And, I'll go 1, 2, 3, 4, 5. I'll go 1, 2, 3, 4, 5. I'll go 1, 2, 3, 4, 5. And basically, well, in this case, they are undirected, so there's going to be quite a bit of symmetry and redundance. But all you do is you find, 2, 3, and 5. Okay, 2, 3, and 5. So all the way down here, I'll write a 1. And then I'll find 1, 4, and 3. And so 1, here, 4, and 3. All the one here's a 1. So all the permutations as well, because these are directed, or we can just make them tuple hyperedges if you want, and then it will just be 2 1s, and everywhere else there'll be zeros, right? And it'll be a pretty sparse. It will be a pretty sparse array. The thing is, it will have a cubic arrays or structures, or cubics. So we could call this the adjacency adjacency cubics. Okay, right. So these are adjacency arrays, right? Because they clearly are capturing, arrays are good at capturing the adjacency information at a given arity. But the problem, of course, is that a hypergraph, I always say that a hypergraph is not only hyper in one sense, it's hyper in 2 different ways. So a hypergraph is hyper in the sense that you can go beyond pairwise connections, or else than, other than pairwise, because you can also go to unary. But it's also the fact that you mix higher arity connections, connections of different arities together, right? So a hypergraph could be, in the same set of vertices, could be something like this, have an undirected here, a unary there, something ternary over here, might be something undirected over here, maybe some other unary over there, you may have several things. So the hypermatrix, our working definition for hypermatrix, what we call the adjacency hypermatrix, it's simply the poodle hypergraph, yeah. It's simply the sort of collection of all the adjacency arrays, right? So you would have something that looks like 1, 2, 3, 4, whatever, 0, 1, 0, 1, 0. Then maybe some direct sum, formal direct sum, it doesn't matter. You could just write like an ampersand or whatever you want here. Then something that is 5 by 5, 1, 2, 3, 4, 1, 2, 3, 4, plus something that is cubic, 5 by 5 by 5, right? 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, right? So this is 0, 1, 0, 0, 1, 1, 0, whatever, right? as you expect. So this is 5, this is 5 by 5, this is 5 by 5 by 5, and so on, right? Higher arity edges will have higher things. Now, the question of that we will cover in the next Explore and Learn is, matrices have algebra, right? That's why they were discovered or invented back in the day. In the 19th century, they were sort of extracted from determinants. Actually, funnily enough, if you ever have any interest in the history of linear algebra, determinants were first. So normally today we learn determinants from matrices, but historically determinants came actually quite a lot earlier than the abstraction of matrices. But they were just abstractions of this idea of subspaces and solutions and so on. But it turns out that they have a natural compositional structure, meaning you can add two matrices together and it means something. You can multiply two matrices together and it means something. So obviously in yesterday's live stream on infogeometry, we were sort of recovering this theme, and it was very appropriate that today we're going to give you the sort of more groundwork for that sort of ideas. But that's the main message that I want to convey here before we close, is that identity matrices are good because they have algebraic structure, because it is very efficient and obvious and clear algorithmically what to do with them in an algebraic sense. We can multiply them, we can take some padding and then do some eigenvalues solutions and things like that. It's something that is very efficient and well understood. So the idea of adjacency hypermatrices or hypermatrix algebra in general is to try and get an idea of the algebra of this more this thicker or richer beings that are not just rectangular matrices. So rectangular matrices, this is very familiar territory. This and this is very familiar territory.
So almost all of linear algebra is on matrices, right? Is that a correct thing to say?
It's the correct thing to say in the sense of matrices, but a lot of linear algebra actually uses tensors.
Okay.
Which, when you express in a basis, will look like these QBCs or higher order arrays. But it's very important to understand that you can define a lot of operations on these hypermatrices, on these higher order arrays that seem to have no connection to linear algebra, and nonetheless are perfectly well defined, right? And so that's kind of maybe a publicity slogan for people who might be interested in the higher arity project that I'm working on alongside the infogeometry and all the other things that we do at the institute. But that's one of the main problems, that the natural algebras of these QBCs, for example, are not well understood. And this is the perfect point to plug the Hypermatrix workshop. So the Hypermatrix workshop that is happening at the end of the month is it's a meeting of cutting edge researchers in all these active areas of work in algebra, hypergraph rewriting, category theory, complex systems, network theory, and so on, that works towards finding what the algebras are in this higher order settings, right? But as a concept, this is what we wanted to encode, and so next time we will work towards connecting the algebra of matrices, which if you went to high school and you did your linear algebra homework, you might remember. We want to connect that kind of matrix algebra to some constructions in graphs and hypergraphs and those kinds of objects. So that will be the next one. Maybe we will do a general one on rewriting, and then we will do the algebra rewriting duality, which is maybe a bit more advanced sounding, but actually it's quite easy to understand once you have the basic ideas clear in your head. So I think this is a good place to stop. That this is a good introduction perspective to what hypermatrices are, and or what motivates them from hypergraphs, and otherwise what arrays are, and the notion of matrix in a more sort of neutral and foundational way, so that everyone has a clear mind. So I don't know if there are some comments, questions, some.
Yeah, there was one cool little picture that Richard pasted
Oh,
for us.
Carlos just mentioned the word determinant, and I was like, oh, I remember some cool things about it. I don't think it's really related because he was sort of, but it's, yeah.
I'll paste it over here. Does this, yeah. I'm gonna bring up quickly the picture for the Hypermatrix workshop. And then what I wanted to say on that was, is it fair to say that there are limitations to linear algebra in terms of going up dimensions?
Again, terminological point here, dimensions in linear algebra normally refer to the number of elements in an array, right? So in for example, in the list case, you would call that the dimension. You would say you can express your vectors as one arrays of length 3, you would call that the dimension of your space, right? You would say that your space is 3-dimensional, which is, the usual X, Y, Z coordinates that people refer to, Cartesian or whatever. That's kind of the geometric notion of dimension. And in linear algebra, that is abstracted as the number of basis elements that you need to express vectors as linear combinations. That's the notion of dimension. So I guess the word that you are going for is arity in this context. Again, and then the answer would be not really, because in linear algebra, arity is very easily generalized, and the higher arity generalization of a vector is a tensor, is what people call a tensor. So but this is in the context of linear algebra. So higher arity vectors essentially are tensors, and which are sort of this very specific linear theoretic, linear algebraic thing. However, what linear algebra struggles with is with incorporating the meanings or the algebras of higher arity arrays into existing frameworks. So as you will learn from what we say in the Hypermatrix workshop, both you guys here and the audience, you will see that, or if you remember from last year, you will see that there are very natural minimalistic looking operations that can be defined at the level of hypermatrices, at the level of QBCs more specifically, that don't admit a linear algebraic interpretation. And that might sound a little bit disconcerting, thinking, well, if you use indices, then surely you're doing some kind of matrix multiplication and there's should be something like that. So that is kind of true, but at the same time, at a technical level, we don't know what kind of mathematical framework captures these operations, these higher arity operations with higher arity arrays. So things like things that we've been studying, like Zapata-Carratalá product, and all these generalized algebras that are ternary and higher for QBCs, right? So just as a sort of a word of announcement that's going in that direction. But as an introduction to hypermatrices, I think this is plenty. And then we will if someone is hungry for the algebra part, because I didn't really speak of the algebraic part, so how you combine these things, what are the natural operations defined on them, it's because we are waiting to present them to make the connection to hypergraphs directly. So for that, we need to do some introductions to rewriting and to the more rewriting component of hypergraphs, and then hopefully the picture will be complete in maybe 2 or 3 sessions. We can get a complete picture of where this is going. But I think as a primer on these notions, this is quite satisfactory.
Okay. Cool. So thanks for that, and yeah, thanks for the fellows who's joined us today. I've definitely got a greater appreciation for hypermatrices, and I think the main takeaway for me is that there's algebraic or even just mathematical importance behind these objects compared to how you would just use them in a conventional software development sense, or when you're talking about these conceptually. They go quite deep when you try to think about things at a foundational level. So just getting a bit of a appreciation for that was important here. And why it is important is because when you're trying to draw these, or I assume why it's important is because when you're trying to draw these parallels between hypergraphs and hypermatrices, those more foundational definitions become important. Oh, Carlos maybe hit the exit button.
or maybe crashed or something because I don't know.
Yeah, so maybe just to end up on that, Richard, yeah, would that be an accurate assessment of what I just said there?
Well, I mean, I think as the difference between like a multi-dimensional array and a tensor or something is that, yeah, they like come to life with their mathematical properties and algebraic relations and so on. Whereas, you know, you can sort of do anything you like to a list and break all the rules. It's a difference between data and yeah. Sorry, my Discord or something keeps
No,
making
that's
noise.
yeah, it's Carlos just saying his laptop did crash, so that's the reason he.
Okay.
Yeah, that makes sense. Nick, some closing thoughts from your side?
No, I guess I'm looking forward to more development of this.
Yeah, no, it's really interesting looking at trying to define these things mathematically. It's content that's quite rare, I think, to find on YouTube specifically, is the nitty-gritty of these things. And for me, just realizing that there's a difference between a tensor and a hypermatrix, like what are those differences? If you can describe that, you can feel accomplished. So good. Okay, thanks everyone, and we'll catch you next week. We'll announce what the live streams are on Monday. So yeah, join the Discord or just stay tuned, subscribe on the YouTube channel so you can get the notifications, and we'll set up the live stream. So normally every Monday you'll know what's going to be coming for the week ahead. Great. All right. All the best. Bye for now.